Welcome students. So today we are going to discuss about modeling with first order differential equations. So as you have seen in chapter 1, recall the key steps of modeling are: first you start with an assumption, then from assumption you go to the mathematical formulation, and then after the formulation you solve the differential equations, because we are modeling with differential equations. And once you solve the differential equations, you study the solutions. And then after studying the solutions, after you get the solutions, you check whether the solution matches with the model's prediction with known facts. And if it doesn't, then it should basically give you new set of assumptions, or it should modify your existing assumptions. So let's go through two examples trying to illustrate this mathematical modeling process. So first one is a chemical mixing problem. So let's read this problem. So at time t equals to 0, a tank contains Q0 kg of salts dissolved in 100 liters of water. So you have basically a tank, and it has basically what? It has Q0 amount of salt. Now assume that the water containing one fourth kilo of salt per liter is entering the tank at the rate of R liter per minute, and it's well stirred, and the mixture is leaving the tank at the same rate. So find the initial value problem for the amount of salt Qt in kilograms present in the tank at time t. All right. So let's draw it. So basically the idea is the salt is entering in, so salted water rather, in, and then basically what is happening is the salted water is going out, of course of different concentrations, right? So salted water out. So now let's try to do the first step. Well, I'll just fill it a bit so that it looks okay. Now let's try to see what are our assumptions here. So from assumptions above, what do we have? The water is entering, water is entering tank with concentration of 1/4 kilogram per liter at the rate of R liter per minute, right? So here, okay. And then, so that is assumption one. Assumption two is that the water is well stirred. Okay, so there's a well stirring happening, well stirring happening, right? And third, of course, the salt cannot be created nor be destroyed in the system. We are not basically talking about any chemical reaction or whatever leading to the creation or destruction of salt for that matter. So now let's determine, so let's make a mathematical formulation out of it. So, so let's determine the rate of salt in. So at what rate is salt coming in? So one, determine the rate of salt in, the rate of salt in. Now let's call it as R in just for short. So R in is basically going to be concentration of salt, right, in per liter, in 1 liter, times how many liters are entering in, right, times the rate of water in, of water in. So the first one is 1/4 kilogram per liter times, now how many liters of water are coming in? R liter per minute. And that is going to be R/4 kilogram per minute. So this is the amount of salt entering in the system or in the tank. Now let's determine how much salt is leaving the system. So now, so let's determine the rate of salt out. Now, the rate at which the water is leaving is the same rate as the water is entering the system, right? So it's R, right, liter per minute, multiplied by what is the concentration of salt. So the water is well mixed, and then so multiplied by the concentration of salt, right? Concentration of salt in the tank. Now, how do we measure the concentration of salt at time t? So Q of t, your function, is basically the amount of salt. Here, if you see, it says amount of salt in kilogram in the tank at time t. So let Q of t represent the amount of salt in the tank at time t. So now what is the concentration then? Then the concentration of salt, then the concentration of salt is, now note that this Q of t salt, kilogram, Q of t kilogram of salt is mixed in 100 liters of water, right? So basically the concentration of salt is going to be Qt divided by 100. And this is measured in kilogram per liter. Therefore, the rate of salt out is going to be the rate of salt out is going to be what? Is going to be R liter per minute multiplied by Q of t kilogram per liter, right? So so it is basically the rate out plus the times the concentration, right? So this is a rate out. Let's call this as R out for a short. So that is going to be Q R by 100 kilogram. So in some sense, these units are getting canceled, right? So kilogram per minute. So now so how is the concentration of salt changing? So the salt, so rate in minus rate out is what? Is how the amount of salt is changing in the system. So therefore the required differential equation is dq by dt. So the rate of change of salt in kilogram with respect to time is rate in minus rate out. That is same as saying dq by dt equals to what? Rate in is R by 4. I will not write the units, minus QR by 100, right? Where, and this is we are supposed to set up an initial value problem. So we need Q of 0 with Q of 0 or Q of some initial value. Is it given to us? Let's see. At time t equals to 0, a tank containing Q0 amount of salt, right? So tank already has Q0 amount of salt. So Q0 equals to Q0. So this is your initial value problem, which, so you have done the mathematical formulation of it. Okay. So now let's study the solutions to this now. So there are two ways to study the solutions. One is qualitative and the other one is quantitative. So first of all, What kind of differential equation is this? This is a linear first order ordinary differential equation. Yeah. So, right. So linear first order. Now, second thing to study is what is the equilibrium solution? So equilibrium solution is when dq by dt is 0, right? So dq by dt is 0, which amounts to saying r by 4 minus qr by 100 equals to 0, which gives me what? Which gives me q. So cancel r from both sides. So we get q equals to 100 by 4, which is 25 kilograms. So this is the equilibrium solution. Also note that dq by dt, so dq by dt is less than 0 when q is greater than 0, sorry, q is greater than 25, and dq by dt is greater than 0 when q is what? Less than 25. So q is less than 25. So q is less than 25. So these are the qualitative solution. I mean, if you can draw the direction field if you want. So 5 is the equilibrium. So 5 is the equilibrium solution. All right. So when q is, sorry, 25 is the equilibrium solution, my bad. Right. So this is your q, which is the quantity of salt in the system. This is your time t. Now you see that when q is greater than 25, dq by dt is less than 0. So the direction fields will look like that. Draw a few different solutions with different color pens. And if dq by dt is less, if q is less than 25, the equilibrium solutions will look somewhat like this. Going towards equilibrium solution. Yeah, so these different color pens are different solutions, and this is your equilibrium solution. Okay, let's just darken with a different color pen. So this is your equilibrium solution. So this is how qualitatively the solution will look like. Now it's a first order linear differential equation, so we can solve it. All right. So we have what we have. What method we'll use for first order linear differential equation? We have developed the method of integrating factors. So let me write down the differential equation again. So dq by dt plus r by 100, q equals to r by 4. This is the standard form. So your p is r by 100. Your q is r by 4. So let's compute integrating factor mu of t, which is e to the power integration of ps ds. This is going to be integration of e to the power r by 100 ds, and then when you integrate, you have to substitute, which is going to be e to the power r t over 100. So this is your integrating factor, and then the solution looks like, what is the solution going to be? Either you multiply this mu of t throughout this differential equation, or you can use the formula directly. So q of t is going to be 1 by mu t, which is 1 by e to the power rt by 100, or let's just write it on top with a minus sign. So rt by 100 multiplied by integral of q mu t qt. So which is going to be, mu is again e to the power rt by 100. And what is Q? Q is R by 4. And then you have dt plus a constant C. So this is how your solution looked like. Now, if you integrate this, you will see. So in that case, you can see that this is going to be e to the power minus RT by 100 times, what is the integration of this guy? So R by 4 is a constant, can come out of the integral. Integration of this is going to be e to the power RT by 100. E to the power T integration is e to the power T, but you have to divide by the constant. So you have to divide by 100, R by 100. That is multiplying it by the reciprocal of that, which is same as which amounts to multiplying by 100 by R plus constant C. So now if you multiply it out, you will see that these will cancel out. So this R will cancel out with this R. This multiplies and cancels out with this guy, and this multiplies with this C here. So we will get, in the end, essentially, we'll get 25 by, so 100 by 4, which is 25. This guy and this guy will cancel. So we have 25 plus C e to the power RT by 100. Okay, so this is your Q of T. Now we need to determine the C, for which we are given the initial value. So using Q of 0 is equal to Q naught, we will see that we get Q of 0 on one hand is Q naught, on the other hand it's just 25 plus C. So therefore Q naught is going to be, so Q naught equals to, or C, we want to find C, so C is going to be Q naught minus 25. And then when you rearrange the solution, you get Q of T equals to 25 plus C. Instead of C, I'm going to write Q naught minus 25 e to the power minus RT by 100. Okay, so this is the setup. Now, so let's check this model. So we have done solving the solution. So recall the steps were, first was assumptions, then mathematical formulation. Now we have found out the solution. Now we'll basically study, we'll go down and study basically whether it checks. So we'll check the solution with the predictions of known facts. So note that we have already found out that the equilibrium solution is 25 kilograms. Yeah. So note that to realize that, take limit as t goes to infinity of Q of T, which is going to be limit as t goes to infinity of 25 plus Q naught minus 25, right? Q naught from here, Q naught minus 25 e to the power minus RT over 100. So this guy will, because of this term here, as t goes to infinity, this term will go to 0. So multiplication of 0 with Q naught minus 25 will also make it 0. So therefore the limit is indeed 25 kilograms, which matches with the idea that the equilibrium solution is 25. Okay. So this seems reasonable, right? So this seems reasonable that after a long period of time, the original mixture will be replaced by the mixture flowing in the mixture flowing in, flowing in. And so what is the flowing in mixture? So mixture flowing in has a concentration of what? 1/4 gram of salt. So therefore what will happen? Therefore, the concentration will be, since concentration is 1/4 kilogram per liter, this implies the total salt is going to be 100 liters multiplied by 1/4 kilogram per liter, which is going to be 25 kilograms, yeah, which is reasonable, right? Okay. So another thing to note is that as R increases, QT approaches equilibrium quickly. More quickly. Yeah, this matches with our intuition, right? The more we feel at the rate of water at which the salted water is flowing in, the mixture will be quickly replaced by it will be quicker, right? The replacement of mixture, existing mixture with the mixture of water and salt of incoming concentration. So this agrees with our intuition. Yeah, matches with our intuition. All right, now, so next thing is, let's study what are the limitation of this models. Are there any limitations? Well, the one known limitation is that there are no other chemicals except salt, right? No other chemicals except salt, right? And if we have and the concentration at which the, the salt water is coming in is homogeneous, right? So if we had several different concentrations of what? Different concentrations of what? Of salt in, we would need what? We would need system of differential equation. We'll touch on that later in the course. We'll need system of differential equations. So we'll need system of differential equations. Secondly, here we are assuming that there is a uniform mixing. So we can't handle uniform, we can't handle non-uniform mixing, right? So that can't be done, unfortunately, right? Yeah, and of course, we are not taking into account of any chemical reactions that may happen in the tank. So no chemical reaction in the tank is accounted for. Okay, but so this is how we managed to deal with this problem. So this is the model again. This was a model about mixing of salt in the water. Okay. Now let's move on to the next problem. So next problem is the following problem. We have a rocket of mass m is projected upward with an initial velocity v0. So we are assuming that there is no air resistance find the required velocity so that the body does not returns to the earth, right? So this initial velocity with which you hurl the object so that does not returns back is called the escape velocity. So what is this velocity? So that is what we are going to find. Okay. So let's think about it. So this is your earth. This is the center of earth. Let r be the radius of the earth and x be the initial distance at which the rocket is from the surface. So this is your rocket here. Okay. Okay. Let's just make it. Okay. So let this distance be x, right? Let m be the mass of rocket. So this be the m. So let's write down the assumption. R is radius of earth. M is mass of rocket, and rocket is this at distance x. X is distance of rocket from Earth's surface. And one more thing we are assuming, which comes from the Newton's law of gravitation, that the gravitational force, gravitational force acting on your rocket is is inversely proportional to the square of distance from the center of Earth. In particular, you can see that this force f of x is going to be minus mg r square upon r plus x square. Yeah. And when x is 0, yeah, when x is 0, you are on Earth's surface, right? And when x is less than r, less than r, that means it's very small compared to r. This reduces down to f equals to minus mg, because in that case, if x is really very small compared to r, you can think about r square by r square roughly as 1, right? R square by r plus x square as 1. So if x is really small, we get this equals to, this part will be roughly equal to 1. So we get f equals to minus mg. Yeah. Right. So that happens when x is very, very small. So that's what we use for Newton's, the that's what we use all the time about what force is acting on the object very close to the surface of the earth. Okay. So now what do we have? By Newton's second law, by second law of Newton, we get what? We get force is mass into acceleration, which is dv by dt, equals to minus mg r square upon r plus x the whole square. So if we simplify this, where v is the velocity, by the way, velocity of the object, of the rocket. So we get, what do we get? We can cancel these guys off. So note that we can write dv by dt. So we want to treat it as a function of x instead of function of t. So dv by dt is same as dv by dx times dx by dt. But dx by dt is v. So therefore this is equals to v dv by dx. So I want to write the differential equation in terms of x. Otherwise, there are too many variables, t and x. So we get v dv by dx, a replacement for dv by dt on this side, is equal to minus g r square upon r plus x the whole square. And of course, your v of 0, let's call it v naught, some initial velocity. Right. So let's solve this equation. So let's try to solve this differential equation now. So this is a separable differential equation, right? So this differential equation is separable. So I'll replace. So I get whatever has v in it, I'll write it on one side. So v dv equals to minus g r square 1 by r plus x the whole square dx. Yeah. So I move this dx on the other side and integrate it, and the constants minus g and r square are constants, so they can be taken out of the integral. So let's solve this. So we get, so integration of v dv is going to be v squared by 2, which is going to be, on the other side, we get what? We get g r square. What is integration of 1 upon r plus x the whole square? That is going to be, if you use the substitution rule or generalized power rule for integral, so this minus sign, and integration of this guy, I'll write it with a different pen, is going to be minus 1 upon r plus x, and then plus c. So this is my integration in the red, okay, which simplifies, of course, to gr square upon r plus x plus c. Now we need to solve for, let's solve for c. So note that v of 0 is v naught. So what do we get? So v of 0 is v naught. So this equation becomes v naught square by 2 equals to g r square by r plus c. This implies c equals to, so this r and this r will cancel, and then you divide this on the, so bring this on the other side, so we get what? V naught square by 2 minus gr equals to c. So therefore I get velocity as v of x square by 2 equals to gr square by r plus x plus v naught square by 2 minus gr equals to my velocity. And if I simplify it, I multiply both sides by 2, I get vx, multiply by 2, so I get 2 gr square by r plus x. This 2 and this 2 will cancel, so v naught square minus 2 gr. This is my v, and then I take v naught square, and v square, and then I take the square root on both sides. So these are my solutions. Okay. So if r is positive, that means the rocket is rising. And if if negative sign is there, that means, sorry, this is about sign of v. Yeah, if so v is positive sign, then the rocket is rising. If v is negative, that means the rocket is falling. Okay, so this is the idea behind it. Now, the next part is, of course, we wanted to determine the escape velocity of this guy, right? So let's go about that. What we'll do is we will basically try to see, so v naught is such that the velocity v is never zero, right? That's what the escape velocity is. So we want this to be never zero. So what we'll do is the following. We'll see when it is equal to zero. So we'll see when v naught is equal to, sorry, when v of x is zero, when v of x is zero, we get what? We get x will be the maximum height you can get, right? So let's call it at a altitude max. So a stands for the altitude. So max altitude equals to a max, right? So then in that case, we can solve for this. When this is zero, we get this part is zero. So we get what? We get v0 square minus 2gr plus 2gr square by r plus a max must be 0, right? And now from here, we want to find out an expression for our a max. So, well, what you can do is bring this on the other side. So you get, so you can think about this as, you get v0 square minus 2gr equals to 2gr square upon r plus a max with a negative sign. So you want a max, right? So take a reciprocal. So we get, and get rid of the minus sign on the other side. So we get 2gr minus v naught square. This is to take account for the minus sign and then take reciprocal of that. So 1 over that is equal to r plus a max divided by 2gr square. Or if you write it in the other direction, so this would give me that a max equals to 2gr square upon 2gr minus v0 square minus r. And then when you cross multiply and simplify, you get this time this will become, so this is going to be 2gr square minus now 2gr square minus of plus v0 square r upon what? Upon 2gr minus v0 square. That is going to be v0 square r divided by 2gr minus v0 square. So this is your a max. Or rather, your velocity is going to be, so what do you get? This implies your velocity is going to be, so again, multiply on the other side and simplify, you will get that this is equal to 2gr a max divided by r plus. Now, what do you get? Escape velocity. So you get escape velocity VE is taking limit as a max goes to infinity, right? So you want the maximum. What does it mean by escape velocity? It means that the altitude, the maximum altitude should go to infinity. So let's take a max going to infinity of this guy, V0, which is going to be, this will become 1. So you get square root of 2gr. So the escape velocity is 2g, v equals to square root of 2gr. So that's how we found out the escape velocity. Now, what are the limitations of this model? So let me just borrow some space here. So what are the limitations of the model? First limitation is no air resistance, right? So no air resistance, right? So air resistance is an important concept here. We should be taken into account. Also, we have constant mass. Right? Typically, rocket loses mass, right? Typically, the rocket will lose mass as the fuel gets burned up. Right? Yeah. So these are the restrictions of the model. All right. So that's it for now. Thank you for your attention.